Welcome to Automated Visual Software Analytics. This part is about cyclomatic complexity. We will give a definition of cyclomatic complexity, we will show some examples of cyclomatic complexity, and we will discuss the rule in software analytics. Cyclomatic complexity is a quantitative measure of code complexity. It was originally developed by McCabe. For that reason, it's also known and called McCabe metric. The cyclomatic complexity is defined by the number of linearly independent paths of the control flow through a given source code unit. A source code unit may be, for example, a function implementation, a method implementation, a class, or even a module. The cyclomatic complexity represents an upper bound for the number of test cases that would be needed to fully cover all branches of a given source code unit, because it calculates the number of possible flow patterns through that unit. Cyclomatic complexity is computed by static analysis of the source code. Let's look at the definition. For a given source code, we build the control flow graph. The control flow graph is a formal model that consists of nodes and edges. The nodes represent the entry point, the exit point, and all decision points. Each node is connected by an edge or more edges to, according to the flow, to other nodes. So the control flow at the end consists of a set of nodes and a set of edges. The cyclomatic complexity now can be calculated as follows. It's the number m that results by calculating the number of edges minus the number of nodes plus 2 times the number of connected components. Let's see some examples. Here we see a simple linear control flow in a method. Basically 3 assignments, 3 statements are given there. The corresponding control flow now consists of the entry point, 1 node, the exit point, another node, and 3 nodes in between. You can see the linear flow. So we have 5 nodes and we have 4 edges. The resulting cyclomatic complexity is now calculated by 4 minus 5 plus 2 times 1, that is 1. The cyclomatic complexity of a linear control flow is always 1. Another example. In the implementation shown here, we have an if statement. That's a key difference to the last example. And the control flow that corresponds to this implementation consists, once again, of an entry point, an exit point, some decision points in between, and the if statement that somehow branches, that represents a branch in the control flow. If we count the nodes, we end up with 7 nodes, with 7 edges. So the cyclomatic complexity results to 2. Any implementation that is linear but has, for example, 1 if statement has cyclomatic complexity of 2. If you have more if statements, accordingly the cyclomatic complexity increases. Let's see a more complicated example, an implementation that consists of 2 for loops within a main function. So we have 6 nodes in total, 7 edges, and the cyclomatic complexity results to 3. What we see from these examples is that all potential flow patterns through a code unit are represented by the formal flow graph, and the cyclomatic complexity results from analyzing the number of nodes and edges of this flow graph. What are the applications of cyclomatic complexity? What is the rule in software analytics? How can we interpret the results of cyclomatic complexity? If the number of linearly independent control flows exceeds a certain number, so if the cyclomatic complexity becomes large, for example 10 or 15, it becomes increasingly difficult to comprehend the control flow. So this measure for complexity refers to how good can we comprehend a given control flow. Experience shows that source codes with a high cyclomatic complexity tend to degrade over years, are hard to test, are hard to maintain or troubleshoot, and high cyclomatic complexity also indicates how likely the code will be to produce errors. Taking into account these characteristics, the application of cyclomatic complexity or McCabe complexity measures include that we can limit the complexity during program development to an agreed maximum, for example 10, but it's dependent on the project and maybe on internal rules what is considered the maximum of cyclomatic complexity. It also sometimes depends on the type of software you are developing or the type of system parts that are considered. So this number can vary, but 10 or 15 seems to be, in practice, a good upper limit for cyclomatic complexity. Cyclomatic complexity helps to identify parts of the source code with high complexity for redesign and refactoring. So it's an immediate consequence if you identify parts having a high cyclomatic complexity, then most likely these are the parts that should be redesigned or refactored soon. To summarize, the cyclomatic complexity represents a fundamental complexity matrix for source code. It is based on a static analysis of source code by counting the number of linearly independent paths through a given control flow by means of a formal model of the control flow graph. The cyclomatic complexity represents a base measure for evaluating the maintenance efforts of a given source code, at least to give a forecast of potential maintenance efforts that have to be spent in terms of redesign and refactoring. The higher the measure of cyclomatic complexity, the higher the costs for understanding and comprehending the source code. The higher the measure, the higher are the risks that source code is faced by deficiencies. So that's the key rule of cyclomatic complexity in software analysis, software analytics. Especially software analytics uses cyclomatic complexity as a kind of key performance indicator, KPI, that evaluates and benchmarks a given complex computer-based system. This concludes this part. Some terminology. We have the concept of control flow graph, a directed graph with directed edges, whose nodes correspond to entry, exit, or decision points of a given unit of source code, and whose directed edges denote the flow of control. It's, of course, an abstraction of the behavior of a given source code unit. The cyclomatic complexity represents a quantitative quality metric whose input are code units and whose outputs are the number of linearly independent paths of the control flow. As further reading, I can recommend structured testing, a testing methodology using the cyclomatic complexity metric. And some remarks: cyclomatic complexity for a whole system provides a general overview of how extensive software maintenance costs and maintenance efforts tend to be. Cyclomatic complexity offers in general a good measure for identifying those parts of your implementation, those parts of your software system that need to be refactored or redesigned, at least in the long run. As a base measure, it can be used also as a kind of weight for other metrics. For example, if you use as another metric the risk, the likelihood of risks, you can correlate the likelihood of risks with cyclomatic complexity to find out hotspots that are risky and need to be redesigned and refactored as soon as possible.